All right, looking at section 3.7, optimization problems. These are applications of derivative and first derivative test. So let's say we have a couple of equations that we can put together in one variable. And if we do, we take the derivative, set it equal to 0, and we can see if that equation contains a maximum or a minimum. And that might be helpful for things like cost functions, or perhaps things like profit functions and things like that. So let's take a look at the notes as far as what are the steps in doing these. So obviously, we're going to use the line of horizontal tangents to locate maximum or minimums, and that's going to happen where the derivative equals 0. So the steps would be the following. Write out the equations using two variables. Maybe you use length, width, or x and y, or whatever comes to mind. Then you're going to figure out which one of those equations needs to be a max or a min. Once you do that, take the other equation and solve for one of the variables so that you can sub in. Fourth step. Use substitution to use your maximum minimum equation. You want to put it into one variable using substitution. After you get your max min equation to one variable, you set the derivative equal to 0. And last but not least, figure out whether you have a max or a min. And you can do that either with common sense if it's a parabola, or you can use the first derivative test or the second derivative test to figure out if you've got a max or a min. Let's look at a couple examples. Okay, the sum of two positive numbers such that the sum of the first and 2 times the second is equal to 100, and the product is the maximum. So step 1, come up with two equations. 1, the first plus 2 times the second one, the sum is 100. We got that down. And the product, xy, is a maximum. So here's step 1. Write it down. Step 2, figure out which one you want to maximize. Step 3, you're going to take the other equation and you're going to solve it for one of the variables. In this case, I chose to solve for x because it was easier than solving for y. Once we have that, step 4, rewrite the product function in terms of subbing in this x here. So I've got 100 minus 2y times y. So my product function becomes 100y minus 2y squared. Now, step 5, you're going to take the derivative and set it equal to 0. So if you take the derivative and set it equal to 0, you'll see that we have a horizontal tangent happening at y equals 25. I went ahead and did first derivative test down here using the intervals to the left and intervals to the right. Plugged those in the first derivative. I found out that 100 on this side gave us a positive sloping interval, and negative 120 or negative 20 on this side gave us a downward sloping interval on this side with my test points of 0 and 30. Now, could I have just looked up here and went, wait a minute, my original function was a downward turning parabola, therefore any horizontal tangent I find is going to be a max. So there's y is equal to 25. And then I went ahead and plugged that back in up here. X plus 2 times 25 is equal to 100, and I can solve for x is 50. And there's my two values. Let's look at one more. This one talked about some sort of fencing where I have 3 widths and I have a length on the top and the length on the bottom, and it said the amount of fencing has to be 200 and maximize the area. So step 1, let's take a look at the two equations. Perimeter, 3w's plus 2 times L, one on the top and one on the bottom, has to be equal to 200. Area, we're going to maximize. So the area of the whole thing is just going to be length times width. So step 2, I'm going to solve one of these equations for L. Step 3, I'm going to plug that L into the other equation. So I've written it with one variable. And actually, I did that, solved one here. And step 4, I write the equation in one variable. Here it is. Step 5, I take the derivative, set it equal to 0. And when I do that, I find W is equal to 33 1/3. Now, again, I guess I can look down here at my test points if you want to, but this is a downward sloping parabola. Therefore, any horizontal tangents we find are going to be a max. So take W is equal to 33 1/3, plug it back into your other equation up here. So 3 times 33 1/3 plus 2L should equal 200. I solve for L. L is equal to 50. I've now found the dimensions of that particular thing. So again, here's some ideas of optimization, and we'll do a bunch of these problems on Monday. Thank you.